Hi, and welcome to video 1 of 2 for Chapter 4. Now, Chapter 4 introduces us to the concept of the second law of thermodynamics and also the third law, which we'll be talking about as well. And it also introduces us to the concept of entropy. In this video, what I'm going to start talking about are reversible and non reversible processes. And then we're going to use those to come up with our first of many statements of the second law of thermodynamics. So, that said, let's talk about reversibility and irreversibility. So, the idea of a reversible process is that you can take Process, there we go. So, the idea of a reversible process is that if you go from one state to another state, we'll say state 2, you should be able to exactly reverse using exactly the opposite steps that you took to get to state 2 to get it exactly back into its condition in state 1. Now, that's a problem if you think about the reality of nature. The world in which we interact, all the things that we interact with have, Avogadro's worth of particles in them. Okay. So, Avogadro's number is 10 to the 23rd, 1 mole. And so, if you think of that many atoms and molecules um, interacting with each other, interacting with your experiment, whatever it is that's going on, taking and moving something from one state to another state, and then reversing it exactly back to how it was before, it really isn't possible. Okay. So, as a consequence, there aren't really any truly reversible processes, at least macroscopic ones that we see. Everything, for the most part, is irreversible. Now, we can use reversibility theoretically to give us a pretty good result in processes that are close to being reversible. Now, that said, if you're dealing with low numbers of atoms and molecules, say 1, 2, or 3, those processes can be exactly reversible, but that's beyond the scope of this course. Now, another example of reversibility would be, let's pretend that you're, we'll say, sitting in front of your computer or your tablet or your phone, and you're watching this video. So you set the phone down, you get up, you, I don't know, walk to the fridge, get a soda out, and walk back and sit down in front of your phone. Now, superficially, to reverse that process, what you would do is you would get up, you would walk back to the fridge, stick your soda back in, and get back, go back to your phone and watch the video. But the issue that you have is getting up from your seat and going to the fridge has you interacting with everything along the way. Okay, as you walk, your feet interact with the floor. The interior of your body interacts with itself. You interact with the air molecules. So just reversing that simple process really is not possible because of how many things that are going on at once and how they interact with each other. You have to reverse the interactions as well somehow. So again, that's the reason why we say, that there aren't any really truly reversible processes in nature, unless, you're dealing with low numbers of them. So, that said, let's talk about the second law of thermodynamics. Now, like I said, we're going to state this a bunch of different ways. And in part, I think that's because, you know, um, this is an often misused and misunderstood law that you see pop up in pop science a lot. So, the first definition we're going to start with is going to be this one, and that's that heat never spontaneously flows from cold to hot. We know heat has a preferential direction of flow. We also know that, through some, thermodynamic processes, we can get heat to flow a little weird. But you never see it spontaneously just reverse. Okay? So the act of going from one state to another state generally doesn't reverse itself in such a way that you would have heat just spontaneously flow from cold to hot. That doesn't make physical sense. Now, using this, what I'd like to do now is to talk about what's called a heat engine. Now, heat engines are things that convert thermal energy into mechanical energy. Now, these are incredibly useful. In fact, the vast majority of the methods that we have to generate electricity come from some sort of heat engine. So, the simplest first step, we'll say, to a heat engine might look something like this. You have a source of heat, and then you have a place that has a lower temperature so that you can get the heat to flow. Now, somewhere in the flowing process, we're going to take some of that energy of flow, some of that kinetic energy, if you want to think of it like that, and we're going to make it do work for us. So, steam is the most common thing that's used to do this. So let me just sort of build, our sort of first step. I call it a first step because it has to be a continuing process if you want it to be efficient. Not efficient, but useful to us, I guess. So let me just sort of make my little heat engine here. Oh, why is going to be problems with that? There we go. Weird. There we go. Let me touch this up just a little bit. Boop, boop, boop. So let's think of steam, just as a simple example. So here we have a high temperature. As a consequence, we're going to call the heat energy here QH. Over here we have a low temperature. And we're going to call the heat that's present here Q sub C, actually, I think is probably a little bit better. So hot and cold. Now, let's pretend this is steam. So we have some sort of pipcock right here, something that seals this container off. We open it up, and because this is, a place of low temperature, steam is going to flow this way. So this is the direction that the steam is flowing this way, from hot to cold, like this. Now, here, what I'm going to do is I'm going to put a set of propeller blades. And these things are attached to a shaft that exits our device, like that. So what's going to happen is as the steam blasts past this, like this, it's going to cause our propeller to turn. As the molecules of steam hit the propeller and sort of transfer a little bit of momentum to it and cause it to rotate. So what ends up happening here is you get rotation, and we know that if you have rotation present, you have kinetic energy, and we can use that, mechanically. So here's your mechanical work. So Ideally, what you would like would be this difference in temperature, whatever that change in temperature is, that change in heat, rather. Okay. This would 100% go into doing work, is what you would like. Now, it never goes in 100%. And we'll be talking about that later. So this is one step, because in a closed cycle, what you would like would be to be able to bring the steam back over here, reheat it, and then continue this. So it's a closed system. Okay. Now, if this were a reversible process, which we're going to assume just for the moment that heat engines are reversible things, just to make our life easy. If it's reversible, that means that your initial temperature and your final temperature end up being the same through the process. So if you think about, for example, the first law of thermodynamics, if you experience no net change overall in temperature, this is zero, so your internal energy doesn't change, which means that you want all of the heat to go into work, which is basically what this says right here. Now, if I were to divide both sides by QH, that's what I get right there. We call this efficiency. And usually a lowercase e is how we denote it. So just to show you, this would be 100% efficient if if QC here were zero. If there was some way in which we could take and we could dump all of the energy here over here, you would have 100% of the energy being transferred. Your efficiency would be 100%, because in that situation, that would require that QC over here be zero. Now, for reasons that I'll be talking about, between this video and next video, that's just not possible. And so you never see 100% efficiency. You never 100% would be an E of 1. Okay, and that's another way that you can state the second law of thermodynamics. So another way would be there are no 100% efficient heat engines. Okay. Now, so let's just work a simple example. Here I have a car that has an engine that's rated at 255 horsepower, and it's 30% efficient. Just for point of reference, an engine in a car is a thermodynamic engine. It's a heat engine. Okay. What you do is you use gasoline that's been vaporized into air. You ignite it, and you use the heat energy from that to do work on a piston. Okay. So you're actually using thermal energy to do mechanical work, but there's a lot of leftover heat energy that ends up being dumped into basically these little channels that run through your engine that carry coolant. Okay, so the idea is that you're trying to offload the heat into the coolant so you literally don't melt your engine. Okay, that's one of the reasons why if you ever run out of coolant in your car, you get a problem. It's also one of the reasons why if you ever ridden a motorcycle that's not water cooled, that it'll overheat if you're stationary in hot traffic, because there's just no efficient way for it to dump heat energy. Now, we're also given here that our engine is 255 horsepower. So that's a power rating. Now, conveniently enough, though, we know the relationship between horsepower and useful power to us, and that's that they're 745.7 watts for every 1 horsepower. So if you convert that real quick, it's 255 times 745.7. That ends up being about 1.9 times 10 to the fifth joules. Okay. Now we know the efficiency here. It's 30% efficient. Now, the other 70% of this energy is going into frictional loss due to the fact that the components inside your engine aren't perfectly frictionless. It's going into thermal energy that leaks out into the environment because your engine block is in contact with the air. It goes into heat that goes into the coolant in order to get dispersed into the environment. Okay. So, that said, what I want to do is I want to find how much work is being done by this engine in a minute. So, our time here is 1 minute or 60 seconds. And I also want to find what the minimum heat discharged into the air, and really that should be everything else here. Okay. So, what we're looking for when we ask for that is QC. Okay. That is the thing that's receiving the energy. We're looking for QC. So, work is pretty easy because we're given power. Power, if you want to think of it, it's just work over time, or not. Work over time rather. So here, work is just power times time, which would be 1.9 times 10 to the fifth joules times 60 seconds. So if I take what I got before, multiply it by 60, I end up, if I carry this out to the precision end of my calculator, with about 1.14 times 10 to the, let's see, is it 3/6 7 joules. Okay. So I see 1 sig figs in the efficiency, 1 in the time. So this would be about, 1 times 10 to the 7th joules. All right. Now, so to find QC, though, that is the minimum heat that's being discharged into the air, what I want to do is I want to look, at our equation over here for efficiency. So our equation for efficiency says that it's 1 minus, QC over QH. So really what we're trying to find here is knowing, QH, which is what this is. Okay. We're trying to find QC. So, we just solve for it. The efficiency times QH is equal to 1 minus QC. So, really, QC is just equal to 1 minus the efficiency times Q sub H. Or 1 minus the efficiency is 0.3. It's 30%. Remember, it's fractions of 1. 1 minus 0.3 times, 1.14 times 10 to the 7th joules. So when you do this, you end up with 3.42 times 10 to 10 to the 6 joules. So this right here is your loss. It's negative. So, the discharge, the loss into the air ends up being something like you know, minus 3 times 10 to the 6 joules. All right. So, what I'd like to do now is to uh, look at other types of heat engines, specifically two that we're intimately familiar with. One of them is a refrigerator. And the other is something called a heat pump. If you live in a house that's relatively recent or it's had its air conditioner replaced, say probably within the last 10 years, in all probability, this is what you have. You have a heat pump in your home. Now, in both situations, if I wanted to know how good these things worked, I could define something called a coefficient of performance. And basically, in both situations, what you're doing is you're moving heat or you're removing heat. Okay. So, for example, for a fridge, our coefficient of performance for a refrigerator, which I'll call it a case of R for a refrigerator, is going to look like however much heat that's been removed from the area that we're trying to cool over how much work it took to do it. Okay. For a heat pump, I'll call it, kappa sub P for pump. It's basically the same thing. It's going to be the heat moved over work done. So let's talk about how these things generally work. And I'm going to use a refrigerator as an example, but heat pumps are basically the same. So, so let's pretend. Let's pretend that this right here is, where all your food is. This is the area that you want to cool. So typically, what you have inside this area are a series of tubes that carry coolant through it. Okay. Usually, this has got a lot of surface area to it. It's a pad of some sort, perhaps. Um, and the idea is that you have very cold stuff move through here. So if you think about this, if you think of TC as being the temperature of your coolant entering, is the cold temperature, this would be um, the temperature of your fridge, which is going to be warmer than that. So the fridge is going to have a greater temperature than whatever this is. So what happens is as this cold coolant passes through, it picks up heat and it gets warmed up. Okay. Now, so what you do is you take this and you put this coolant, which at this state a lot of times is a gas, and generally it is, and then you compress it by doing work. This is a compressor. Now, when you compress it, it heats it up. Okay. And so what you do is you take this hotter coolant and you pass it through a grilled thing called a radiator. All a radiator here is a tube generally that has got a thin sheet of metal attached to it, and what that does is to allow the heat to leave that coolant or at least much of the heat to leave the coolant into the environment by heating up the metal and by having a huge surface area. If you remember, for example, the Stefan Boltzmann law, which says that the power emitted is equal to sigma epsilon A times T to the fourth. The bigger the area, the more emitted power you have here. So that's the goal here, is to emit the stuff away with a huge surface area. That's the reason why radiators in your car, or the radiator on your refrigerator, or if you were to go outside and look at your heat pump or your air conditioner, it has an enormous radiator on it. Basically, what you're trying to do is you're trying to get the stuff as close to the background temperature, the temperature of um, your environment as you possibly can. So what this does is to cool it down. Now, it doesn't get it as cold as what it was when it entered the fridge, but it does get it cooler. Certainly cooler than it was when I compressed it. So here it is, the stuff is passing through. And what I'm going to do now is I'm going to put it into a void, a chamber. Okay. And so I have this sort of compressed, at this point, probably a fluid, compressed fluid. So it's gaseous is here. It becomes a fluid as I compress it. And I'm going to let it expand out. Okay, so it expands. Now we want to make this as close to adiabatic as possible. If you remember, adiabatic means dq is equal to 0, which means that du plus dw is equal to 0. So what's going on here is that your gas is doing work to the environment. So as a consequence, since this is positive, du goes down, which means it gets very, very cold. So what I do then is to take this expanded cold gas, which at this point is very cold, it may even condense into a liquid, and then I want to run it through my fridge. So that's your complete cycle. Is basically you take your warm or cooler that's left the fridge, you compress it, you pass it through a radiator. Now it's in a liquid form. Okay, you let it vent off all that heat. That's a consequence of the heat that was inside the fridge, plus in a big way the work that was done. So you dump a lot of that out into the environment to get rid of it. And then you stick it into a chamber that lets the gas expand. And as a consequence, through adiabatic processes, it cools down. And then you take the resulting cool stuff and you pass it through the fridge again in order to cool it down. So heat pumps basically work the same way. For example, in your house, in your air conditioner, if you were to go outside and look at your, what do they call them? Ours is in a garage. I can't remember the name of it. It's the stage. Second stage of the air conditioner, maybe. I can't remember. But if you go out there and you look at it, that unit has got a lot of coils on the inside, and it's basically doing exactly the same thing, except there the heat is being vented outside of the house because, if you use this model, basically the inside of your fridge is your house. So you want to dump the heat outside of your house. Okay. So if you think of it like that, then, like, for example, with the fridge, the heat that we want to remove basically is just, what's going on in here. We want to remove that. And the work that's being done is literally just the difference, as per efficiency. It's the difference between the two. With the heat pump, we want to do this. This is for heating. So what I'd like to do now is to take a look at something called the Carnot cycle. Now, the Carnot cycle was postulated by a French physicist named Carnot to be the most efficient process that you could see, using thermodynamics. So the idea here is a combination of isothermal and adiabatic expansions and compressions. So if you remember the first law of thermodynamics, it says that dq is equal to du plus dw. And in an isothermal standpoint, that means that T is constant. And if that's the case, that would be du equals to 0. So for an isothermal process, the heat that is going into or out of the system is related directly to the work. Now, in an adiabatic situation, though, what happens is that dq is equal to 0. And in that situation, du is equal to minus dw. All right. So basically, Carnot's cycle for a heat engine consists of 4 steps. The first step is you taking your gas and placing it in contact with the environment such that heat flows in, and it's going to be hot. So in your first step, what you're using is QH from outside to maintain an isothermal expansion. So what happens here is you add your heat in. We start off with our initial volume, whatever it is, and we're gonna heat and transition, gonna cause it to expand to go to a new volume, which I'll call V2. And since QH is just going to equal to the work, if you look up the work or you go back and you rederive the work, we'll call this W1 since it's the first step. For isothermal expansion, it's going to look like N times R times T. Now, the T here is going to be the temperature of the reservoir, but also the temperature of the gas, because we're using the reservoir's temperature to maintain constant temperature here. So we're going to call this T sub H, okay? The natural log of our final state, which is V2, over our initial state, which is V1, okay? Now, the next thing we're going to do is to basically turn off the heat and let our gas expand adiabatically. So now Q is equal to 0, and we're letting adiabatic expansion happen. And adiabatic expansion. In this case, what we're doing is we're going from volume 2 to volume 3. And, we have relationships between temperatures and volumes here. Since we're at TH right now, we're going from TH to a new temperature, which, I'll call T3, just for lack of a better way of describing it. And so here, TV to the gamma minus 1 is constant. So it would be, TH V2 to the gamma minus 1 is equal to T3 V3 to the gamma minus 1. Now here's the deal though. Our temperature here is going, our final temperature rather, is going to be held constant, because what we want now to do is to isothermally compress this. So now we're compressing it isothermally. So we're going to place it in contact with a cooler heat source and let that handle the work. So now it's doing work to it, right? So this is going to be W3. NR, I'm going to call this T sub C since this is our cold reservoir. Natural log of, now we're going to get to the volumes here in a moment. But what I would like to point out here is that is it T3 here? This is really just TC, okay? Now, so here we're going from our volume V3 to a new volume V4. All right. So this is going to be adiabatic compression. Now remember though, what's happening now is work is being done on the gas to compress it. So this is negative work. Okay, so our work here is going to be negative. Now for our fourth and final step, what we're going to do is we're going to let this adiabatically compress. Now, what's happening here is we're going from our temperature that we have now. Remember, this is isothermal, so TC in step 3 was held fixed. So we're going from TC here back to our original state, which was TH. We're also going from our new volume V4 back to our original volume V1. So we're taking it back to the original state. So again, if you look at our adiabatic equations and note the fact that TV to the gamma minus 1 is constant, then what that means here is that TC V4 to the gamma minus 1 is equal to TH V1 to the gamma minus 1. Okay, so we have a full cycle. Now, if I were to look at this on a PV diagram, you can kind of get a feel for what's going on. So we start off, we'll say here, this right here is state 1. And we isothermal expand. Isothermal expansion looks a little bit like an exponential, like that. So we're going this way. Then we're adiabatically expanding. So as you can see, our volume's getting bigger. Now our adiabatic expansion is going to look something like this. So we're going this way to state, from state 1 to 2, from state 2 to 3. Now 3 is compression. This should be adiabatic compression. I don't know why I put this. This is isothermal. Sorry about that. Anyway, this is isothermal compression. So anyway, so what happens is we go from here to step 4, and then we compress adiabatically. Like that. Back to 1. So it's a closed loop. So what that means is my change in internal energy overall is going to be 0. So now let's take a look at the efficiency. The efficiency here is going to be 1 minus QC over QH. And what I'd like to look at right now is just this ratio QC over QH. So as written, at least superficially now, QC is negative and QH is positive. So I'm going to put a minus sign out in front. Just go ahead and pull in that negative sign here. QC is NR TC, the natural log of V4 over V3. And QH is NR TH, the natural log of V2 over V3. So what I'd like to do is to clean this up a little bit, and I'm going to use the adiabatic expansion and compression to do that, specifically noting that this deals with TH. This is technically on the right-hand side over here. This is TC. This over here deals with TC and TH as well. So I want to try to get a relationship between the changes in volume here. So using this, I'm just going to write this over here. TC V4 gamma minus 1 is equal to TH V1, gamma minus 1. Now, if I look at this one here, if I divide this equation by this equation right here, I'm going to put Tc V3 gamma minus 1 on the left-hand side. And on the right-hand side, I'm going to put Th V2 gamma minus 1. So the THs and the TCs cancel each other out. This is raised to the gamma minus 1. This is raised to the gamma minus 1, which gives us a relationship about the stuff on the inside. And that is that V4 over V3 is equal to V1 over V2. Now, take a look at what we have here. This right here for QC is right here is V4 over V3. This one right here is for QH, V2 over V1. V2 over V1, this should be V1 right there. So I notice a V2 or V1 over V2. See, you got V4 over V3 here. But if you take a look at these things, they're almost the same. If only I could flip this. And I can. And I can do that by using the properties of natural logs. For example, minus 1 times the natural log of A over B is the same thing as the natural log of A over B raised to the minus 1 power. So whatever sits out in front, you can pull in. And, when you raise something to the minus 1 power like that, what you do is you invert it. This flips it and it causes this to be B over A. And lo and behold, there's a minus 1 sitting out in front. So if I take this minus 1 and I put it here and I let it flip, okay, and I'm going to go ahead and cancel out the NRs right there. So I would have then a TC natural log of V4 over V3 on the top, and on the bottom I would have a TH natural log of V2, or rather V1 over V2 now. And the thing is V1 over V2 is the same thing as V4 over V3, which means that these are the same. So this is just TC over TH. So what's nice about that is that if you have the Carnot cycle, now if you want to talk about the efficiency of it, you don't need to know anything about the heat. All you need to know is information about the cold temperature and the hot temperature. And to be clear, this has to be in kelvins. Remember, in this form, this is Kelvin. So these are kelvins right here. So you're in absolute. So that's the Carnot cycle basically in a nutshell, right? And what I'd like to do in the next video is to talk about how a lot of this stuff relates to entropy. And I'll see you then.